I'm Valiushko, an open source developer at Amazon MQ for RabbitMQ, and this is how to break RabbitMQ. So we have a customer, technically savvy, big company, with plenty of expertise about RabbitMQ operation. And one day we see their brokers keeling over. Hours of investigation and reports and meetings later, we conclude that there is no appreciable difference in load before and after. Yet we find one common clue: a consistently appearing log message that predicates an immediate and total meltdown of the broker. What was the message? You'll have to wait till the very end to see. I expect this talk to be most interesting to those of you who are using various cloud offerings of RabbitMQ, although the lessons are totally applicable to homegrown solutions as well. I hope to educate and perhaps amuse you, showing what we can and can't do, and what you should avoid doing to keep your broker working. After a bit of context setting, we will go to explore the mechanisms that broker employs to protect itself from adverse conditions. And after that, at last, we will dive into the cases where those mechanisms fall short, with hints on how it can be avoided. So, on to the context. With the advent of cloud, the design goals, architecture, and guiding principles of RabbitMQ have been shifting, slowly but inexorably. Fast drives and fast networks changed the tolerances and design space of the software. But importantly, the cloud changed operators' mindset. A new type of a RabbitMQ admin appeared, where previously one had to understand the OS and the application to set it up for a planned workload. Nowadays, many expect the cloud to provide cookie-cutter instances on a whim. The premise is clear. You do not need to understand how it works. We will take care of everything. But RabbitMQ was first built in a gentler age. Experienced operators, tight vertical stacks, precious physical servers. Everything was done with more care. It is undergoing a rapid transformation to fit into this new world now. RabbitMQ already has mechanisms that it employs to remain stable under adverse conditions, but it must continue to improve them. So what do we get by default when we press that coveted launch button? Typical cluster deployment is a familiar beast. A cluster of 3 nodes running a default vhost with a basic replication policy. We run each node on a middle-of-the-road instance, and we know that replication does not add, but reduces throughput. Our goal here is zero downtime operation. Yet we expect RabbitMQ to be able to handle quite a lot with this setup. We will have many teams in our hypothetical org using the broker for various workloads, so vhosts will be added, with obviously many more queues and users. As a side note, vhosts are another remnant of the ages gone. Rabbit hosts are virtualized already. Wink wink. And we'll point our fleet of hundreds of producers and consumers to ferry data through this replicated and fast pipe. I must say at this point, I will not be explaining the basics of RabbitMQ and AMQP operation, although my hope is the message is clear, terminology notwithstanding. Nor will I delve into the many of the integration woes. Client libraries of all kinds and levels of support are abound, and it would be impossible to cover them all comprehensively. And they do have issues. Just to illustrate, recently our engineers discovered a mistaken assumption in one of the most popular libraries, the Python-based Pika. Contrary to the AMQP spec, Pika assumes that RabbitMQ will blindly accept the connection timeout it dictates. Needless to say, wrong expectations may lead to bad outcomes. Keep your libraries up to date, and if at all possible, contribute to their improvement. So, cutting to the chase, how do we break this setup? Simply put, it's resource starvation. But before we go into the fun part, let's review how does Broker protect itself from this. We have three mechanisms: flow control, alarms, and confirms. Flow control is modeled after the existing QoS mechanism in networks. And it has to be an admittedly complicated mechanism like that, as we have a cluster of 3 instances and there is no telling what path a message will take between being produced to the broker and consumed out of it. There are numerous steps in between, and we have to ensure all of them track their allowed throughput. And so, for every message published, a producer channel has to consume a token. And, simplifying it, the tokens are spawned at and propagated from the consumer channels. Everything on the path, channels, queues, exchanges, participate in this unbroken chain of responsibility. Limiting token production, the application may slow down throughput to a desired rate. In our scenario, we rely on the default flow control settings. It is primarily an internal mechanism, with defaults set by maintainers according to the software architecture of the given Rabbit version. So best not meddle with it. But in order for this system to be of any practical use, it needs to be able to signal the busy status over the network. Rabbit calls this confirms, publisher and consumer side, and it is just that, a way to signal the busy status, all the way from your consumer through the broker to your producer. Being an opt-in feature, far too many users forget to turn it on. Needless to say, it may end in a disaster. Despite the rate limit, if the message backlog grows slowly, the system will still run out of memory. Memory and disk alarms save the day. Set per best practices to below half of the available memory, this alarm will completely stop production if the broker reaches the limit. Remember, alarm state itself is not good. No production means your edge applications grind to a halt, and the broker itself is fragile. But it stands. So flow control and alarms combined, plus the Erlang's famous stability, means broker will never crash due to load. Yet it does. Let's dive into what exactly may go wrong. Some of you may already guess what remains unchecked by the above systems. They do cover the messaging part quite comprehensively, right? Starting with the most common source of resource starvation, channel and connection leaks. are floods in some cases. Failure to properly close a connection or applications that open channels or connections for every message are a sad but frequent sight in our infrastructure. It is, of course, never by design, but far too many times. We have seen client applications doing exactly this and ending up in a very sorry state. To explain, the connection itself has CPU and memory footprint. Every channel, every connection involve an allocation and a bit of work to set up. Thus, despite the best efforts of publisher and consumer confirms, or even the memory alarm, you still, fairly easily, can go out of memory if you spawn enough connections. And there are limits, of course. The problem is in setting them to the right value. You, as an end user, know how many cons the broker should expect. But we, the cloud operators, do not. We must allow some of you, the IoT companies perhaps, to scale up to thousands of client applications. Yet, how can we tell if those thousands will not end up being the final straw breaking the back of an already loaded broker? The outtake is simple. Reuse connections and reuse channels. There are good docs online, but the gist is limit each producer and each consumer to a single connection, and reuse a single channel per thread per queue. Yet, it's rarely the leak alone leading to a failure. No single limit will account for load amplification. And the most prominent amplification factor for all of the above and below is deep queues and large messages. It is not the number or the size per se, but the time to process that one has to be vigilant about. Classic queues trying to sync up massive replicas are simply fragile. And one can limit those as well. A stable broker can handle quite a lot, but it is in everyone's best interest to set sane limits, for when broker trips, it may not stand back up under such load. To reiterate, message count is your fragility metrics. And as the limits go, these are tricky for the operators as well. Limit per queue. How can we tell how many queues a user spawns? Per vhost? Same. Time to live is a great escape hatch, but of course it is not for us to manage. Remember, an empty broker is a happy broker. Another amplification factor, and the hidden cost to pay, is negative acknowledgements. Depending on your setup, you may have zero problems, or spike resource consumption into oblivion. The problem stems from how much a broker may have to do for every NAC. An inconspicuous and tiny for your client app answer leads to redelivery. And since there is no way to block until the NAC job is complete, no publisher confirms, so to say, you may end up with an unforeseen load spike. All that said, there is a continuous effort to make RabbitMQ faster under the hood. We observe this issue less in newer versions, so keep your broker up to date. As well as there are well-understood mechanisms to curb the amplification effect of NACs. Message TTLs, for quorum queues redelivery counts, all the usual suspects. Use them. And for the last, replication churn. So this is the case and the log line that I mentioned in the beginning. As a diligent Rabbit operator, early on, we decided to run a script that would enforce 3-node replication, even if the end user forgets to set it. And then, let's say, purely hypothetically, that one of the teams using our cloud broker decides to run its own script to set replication to 2 nodes. And of course, they do it on a queue with a massive backlog of messages. It's admittedly an odd duck, but this is the most reliable known to me way to shut down the broker. Even manually, changing replication policy from 2 to 3 replicas and back will hang broker only after a handful of iterations. Broker creates a replica, attempts synchronization, and mid-process receives a command to shrink. And if you repeat this process enough, with enough queues and enough data, you inevitably end up with a backlog of massive data replication, an unresponsive broker, and if you decide to restart, lost replicas. There is an obvious way of this, sure, just communicate, right? But it is of course much harder for cloud operators. No easy line of communication, nor a way to anticipate every possible use pattern. This problem exemplifies our penultimate issue, the disconnect between operators and users. This disconnect is part of the new era, unfortunately, but we must work on adapting RabbitMQ to it. To sum it up, none of these cases will alert an experienced operator. There is logic and reason behind them, and a clear way to avoid. Yet we have a limited ability to protect you, and keep seeing them happening every day. On the bright side, in addition to exposing dozens of limits, we are looking for a more comprehensive solution. A mechanism that would allow broker to remain stable under adverse conditions, and a system that would let you both exploit your hardware to the max and remain resilient to stress. It may take form of a more sophisticated aggregate load metrics, or perhaps an expansion of the alarm subsystem. Too soon to say. This is all, and looking forward to talking to you about this in the future.